Okay, we're going to look at a real issue, although we are going to have some fake data to approach it. But in advertising, one of the issues is the message that you're putting forth, is it accurate? So there's been several lawsuits over, for example, this is Minute Maid, a Coca-Cola product, and they were giving this pomegranate blueberry. Notice how the area of the pomegranate's pretty big, and but yet it has like 1% pomegranate juice, something like that. Palm sued them because their original pomegranate juice is 100% pomegranate juice, and so they sued Coca-Cola for false advertising, and then they had to figure out what percent of Coca-Cola's drink really was pomegranate juice. Another one, interestingly, the Supreme Court let Coca-Cola sue Palm back because of some of the health benefits that Palm was claiming for pomegranate juice. So several different lawsuits going on there. This is Almond Breeze. It got sued because only 2% of its almond milk is actually almonds. And the question was, are they overrepresenting what percent that is? So the idea is that advertising is important. We need it to be accurate. As the general public, we deserve to see the accurate representation of what the products we're buying. So here's a question for you. The Reese's Pieces bags that purportedly contain 14 ounces of Reese's Pieces, do they actually have less than 14 ounces of candy in them on average? Is Reese's somehow trying to get away with scrimping a little money, assuming that people aren't really going to measure? So how could we test this? Well, if we could get a random sample off the production line, if there was a lawsuit and we somehow suspected this was going on, we might be able to get a court order for a random sample. And we get several bags of this Reese's Pieces, weigh each one, and then we compare the results to the advertised weight. So let's say we did this. I did not do this. Let's say that we were able to get 100 randomly selected bags, and that our average weight is 13.94 ounces, the average of these 100 bags. And here's our sample standard deviation. Does this give us good evidence that the average bag in general, not just our 100, but that Reese's Pieces Halloween bags in general contain less than 14 ounces of candy, that there's some false advertising going on? Notice that I'm not really concerned if the average bag contains more than 14 ounces. Hey, great for the consumer. Well, probably not in terms of health benefits, but it's not the thing that I'm interested in. I'm interested in false advertising, so I specifically want to know less than. That's going to be key here when we get into step 1. So go ahead, pause the video, see if you can figure out what the null and alternative hypotheses are here. So the null hypothesis should always be mean equals. Null means nothing. So in other words, if there is no false advertising going on, if there's nothing sketchy going on, if Reese's really is giving us 14 ounces of candies per bag, then we would expect the average of the samples that we take to average out to 14 ounces. However, the alternative hypothesis is if that's not happening, are Reese's Pieces bags in general holding less than 14 ounces of candy? And that's why we use the less than here. So this less than translates here, giving us a one-tailed test or a one-sided hypothesis, because we can only reject the null if our value is so low, if our sample value is far enough below 14 that we think it's not just because of the 100 bags we chose, but in general, Reese's Pieces bags weigh less. So you might think right off the bat, well, we have 13.94, that's less than 14 ounces, so we can already say false advertising. No, because we just took a sample of 100 bags. There's always going to be some random variation in weight. It's possible that our sample was just a little bit on the low side. Others of you might say, well, that's close enough that we can right away say there's no false advertising. That's also not necessarily true. Because of how these sample variants will work out with larger numbers giving us more and more precise variance, we can actually have this be good evidence against 14 if, depending on how the sample plays out relative to other sample means. So at this point, we really don't know whether we have good evidence against the null hypothesis, against Ricci's claim. Step 2, what's our alpha level of significance? So we're going to keep a 0.05 unless otherwise told. The critical z, in order to translate that 0.05 to a critical z, we need to know if we're putting that 5% all in one tail of our distribution, or if we're going to split it across the left and the right tails. And because we're doing a less than here, going back to step 1, that tells us we're putting that entire 5% in the left tail. So the only way that we'll reject this null hypothesis is to get a really low sample, just an unlikely low sample of Halloween Reese's Pieces. So because it's a one-sided, you could look up 0.05 in table A and you'd find your z-star of negative 1.64. Oftentimes this is just written as a positive value. But what it's saying is when we calculate our z-value, if it's less than negative 1.64, we're going to reject the null. If it's above negative 1.64, we're going to fail to reject the null. So calculate our z-statistic, p-value. Go ahead and pause the video, try to do this. Here's the data you need again. So putting things through the formula, our sample mean was 13.94. Our sample size was 100 bags. Our null hypothesis mean was 14 ounce. If Reese's really is telling the truth, then the average of all Reese's Pieces bags should be 14. Here's a little twist where we're doing some foreshadowing of what's to come. Notice we don't know the population standard deviation. That would be really hard to get. What we do know is the sample standard deviation. We know that our sample had a standard deviation of 0.25. So I put a little danger flag here. This sample is a miniature version of the population. So if we're going to estimate this sigma, our best guess is our sample standard deviation. However, we know that it's probably not exactly right, and so we're going to have to pay the price for that a little bit later when we get into chapter 17 and 18. We'll talk about that more in detail, of the price to pay for using sample standard deviation to estimate population standard deviation. For now, let's let it ride and see what the calculations do. So we're going to get a negative 2.4 z-value. If we would plot this on a normal distribution, we would get p equals 0.002. This would be the portion of the standard normal distribution that's below negative 2.4. In other words, we look this up on table A, and we would get 0.0082 of the distribution being below a z-value of negative 2.4. Now the question we need to ask ourselves before we actually call this our p-value, first of all, is it the value in the tail or in the body? Well, the tail is the area below negative 2.4. Let me show you a picture. Okay, so we had a negative 2.4 there, and if we look it up in table A, the tail would be the area to the left. So what table A gives us as that 0.082 is exactly what we need. If we had had a positive 2.4, the tail would be the area to the right, and so we'd need to get the area to the left from table A and then subtract it from 1 to get the area to the right in the tail. Here, table A gives us the area to the left, which is exactly what we need for the tail. The other question we want to ask ourselves is, are we conducting a one-tailed or a two-tailed test? If we're conducting a two-tailed test from back in step 1, when we decided on the alternative hypothesis, then we need to multiply this number in one tail by 2. We need to double it. In this particular case, we're just doing a one-tailed test. We're saying, do Reese's Pieces contain less than the 14 ounces, not a different number then. We said less than. That's a one-tail question. So when we get the area in one tail, that directly is our p-value. Next question, what's our decision? So we've conducted the test. Did we get good evidence against that null hypothesis, against Ricci-Pici's claim? So two ways to look at this. First of all, we can look at that negative 2.4. How does that compare to that rejection region we set up in step 2? Remember, we needed to get less than negative 1.64, which we did. Negative 2.4 is out in the tail further than negative 1.64. It's less than negative 1.64. So that means we do have strong enough evidence against the null hypothesis to reject it. We can also look at our p-value here and compare this to our 0.05 alpha level of significance. Remember the little catchphrase, p-value low, null must go. Indeed, our p-value is low here. It's lower than that 0.05 threshold. So this would also give us evidence against the null. These two ways of making a decision against the null should always line up. If one of them tells you to reject and the other one says fail to reject, you need to go back in and look step by step for where you made an error, because they should always line up. So we do reject the null. We have strong evidence against it. And in plain English, what does that mean? Remember, the null is the claim that the average Reese's bag contains 14 ounces of Reese's Pieces. We've got good evidence that that's not true. So our study does suggest that the average weight of Halloween Reese's Pieces is less than 14 ounces. In other words, we do have grounds for a claim that there's some false advertising going on. Of course, this is, let me make it clear, this was fake data, but I think it is worth pointing out that even though that was so close, 13.94 compared to 14, you'd think that that's so close that it's not a significant difference. But because we took 100 bags, that really narrowed our standard deviation. In other words, it allowed us to really accurately portray what we were doing here. And so that's why we were able to reject, even though this is so close to the 14. All right.